If you turn to page 42 in your book, and I'll try to put this up here, you'll see a diagram. See if you can see this diagram here. So you'll see this diagram, which is figure 3.3, and it's actually showing you water in the upper right-hand side of the diagram. You're seeing some water molecules at the boiling point of water, and you see that they're fairly far apart. Then within the range where water is actually a liquid, you'll notice that those molecules have gotten much closer together, ostensibly because of hydrogen bonding. Now, if you look, once you get down to about 4 degrees, you still have liquid water. It doesn't solidify until you get to 0 degrees. But what you'll notice is that there are a series of hexagons right here, this hexagonal arrangement of the water molecules. And I call that to your attention because if you look at that, you'll notice that the spacing between water molecules is actually greater there than it is in the case of liquid water. Because when these things are randomly oriented, when the water molecules are randomly oriented, they can actually get closer together than they can when we actually have ice. And then at that point, the structure is actually frozen out into this hexagonal configuration. And this particular configuration, while it is a relatively low energy configuration, it still has what is, and this is not mentioned in your book, but the difference between water and ice. Both water and ice have hydrogen bonds. Why should they be different? Ice is actually, there's also some additional energy in ice because of the fact that there's it is now locked into what is known as a crystal lattice. And the lattice, this very orderly arrangement of atoms, actually imparts some particular structure and a greater energy content than actually. In other words, it takes more energy to actually break this apart than it does to disturb the bonding, the hydrogen bonding in liquid water. Because in ice, we not only have to break hydrogen bonds, but we also have to overcome the energy of the lattice in order to melt the ice. So these are things that I call to your attention because one of the things that comes out of this is the fact that when we actually have the water freezing, if water were to freeze like other liquid materials do, what normally would happen is we would expect, as I said before, we'd expect as things cool down, the molecules get closer and closer together, and then once they freeze, they usually when they freeze, the molecules are most densely packed together. But in this case, as I've shown you, that in the case of ice, this particular arrangement is such that ice actually has a lower density than liquid water does. So as you know, you throw an ice cube in the water, it floats on the water. And ice is going to actually float anytime you put it onto water. And when ice forms in water, in nature, it doesn't form the way other liquids would freeze, which is because of the density of ice being less than the density of liquid water, which is not the case for other liquids. For most liquids, they will freeze. The frozen material will be more dense, so it will tend to sink to the bottom. So we would expect things to freeze from the bottom up. The bottom would freeze first, and then the layers above that would freeze, and finally the surface would freeze. Well, that doesn't happen with ice. You look at a body of water, anybody that's ever gone ice skating, you know that you get a thin crust of ice on the lake or on the pond that you happen to be skating on, and then if the temperature is cold enough, eventually that layer of ice will get thicker and thicker and thicker. And if anyone's ever been ice fishing, you would know that you actually have to cut, the ice can be quite thick, and you actually have to cut a pretty big chunk out of it. But once you do that, the underlying water is still liquid water. So why is this important? Because if that weren't the case, then what would happen is all the living things that are in that water would probably die every time the body of water froze, because it's very unusual to have any body of water freeze completely. There's always going to be this top surface that's going to freeze, and it will freeze down to a certain depth. If there's sufficient amount of water in there, eventually the thickness of this material is such that it actually acts as a kind of an insulating layer, and it will prevent further freezing from occurring. So that this is one of the things that actually enables the sustenance of life. The fact that in the winter, bodies of water do freeze in that way, and whatever happens to be in there, even though the water might be quite cold, it doesn't freeze completely. So these things can actually survive through these changes.